If there's something on the screen you can't see, holler at me. Okay. All right. So here's what we're going to do. So last time I saw you, last time I talked to you guys, we dealt with some things called gas laws that were basically how do gases behave when you mess with some measurable characteristics. So, for example, if I take a gas in a syringe and I compress it, what happens to the pressure? Okay, those were called the gas laws, and those gas laws are going to be different than today's gas law. Today's gas law is called the ideal gas law. So there's going to be some slight differences, and I want you guys to notice. Uh, in general, there's kind of two main differences. And with the ideal gas law, it is going to be the one that is used if you ever take college chemistry. It's going to be the one where the professors, because they're just like, sneaky little boogers, there's lots of little mistakes you can make. So I'm going to try to point out where to not make those mistakes. Okay, so this gas law today is going to be different than something like this. Okay, so this is Boyle's law from last week. Boyle's law basically took a gas under some initial characteristics or conditions, and we changed one thing and we looked at how the other thing responded. So today's gas law isn't a before and after. Today's gas law is literally here's everything. How does this one thing that you don't know behave? Okay, so there is no before and after. It's kind of just barfed up all sorts of stuff and how does it behave? Okay, so for previous gas laws, we kept one thing constant. In other words, there was one thing that did not show up in any of our previous gas laws, at least the ones that I gave you. Now, there are gas laws I didn't teach you last week. Like I said, I'm trying to teach you kind of the basics at this stage of our class. So the one thing that we did not include in any of our gas laws was moles of gas. And moles of gas is labeled with an N. So it's a little bit different. It's a little bit weird. You'll notice that in Boyle's law, Charles' law, Gay-Lussac law, moles of gas did not show up. Now, there is a gas law where mole does show up, but we didn't deal with that stuff. Okay? Today, we are going to mess with moles of gas. So we're going to throw moles of gas into the mix. So here is a new variable for us, N. Now here's another variable that's we're going to throw in. I'm not going to go into a ton of detail on why we need this. The next one that we use is called a gas constant. It's called the ideal gas constant, and it is labeled with a capital R. And basically, this is a bit of a lie, but this is good enough for us right now. What the ideal gas law constant does for us is it kind of allows us to treat all gases as if they are the same. An ideal gas is not a real gas. It's kind of like making the problem a little bit easier for you. So we can use an equation that is small versus one that's like enormous. Okay. So these are little i's that allow us to use an easier equation. And what we're going to do is factor in the following variables. Okay. So we will have pressure, volume, moles, this weird R value, which I'll talk about a little bit more in detail, and temperature. Okay, so our equation today, when we get to it, will have all of that stuff in it. Okay, before we get to that though, we need to talk a little bit more about what this R is. Okay, and like I said, it'd probably take me a whole class period to talk about where it comes from, why we use it, and all that stuff. Just know that it is factored in to make to allow us to calculate all these things. It's kind of like the missing piece that allows us to put all these things together. Now, R has lots of different values. For us, I'm going to give you 2. And what you guys will learn if you take enough science is that sometimes there's numbers and there's constants, and that's what this thing is. It's a constant. And constants have really weird labels. And they have weird labels because they want you to be able to calculate one of the 4 things in here. So I'm going to give you guys a couple of values. Sometimes for R, you're going to use 8.31. Now, the labels for R when you use 8.31 are kPa, liters over moles Kelvin. And you're probably looking at that going, what is going on here? I don't want you to freak out about this, okay? I'm going to show you the other value for R, and we're going to talk about how and why it's different. So here's the other value for R. The other value for R that we can use in our problems is 0. Don't forget that 0. That's huge. That's what everybody does wrong when they first screw this up. 0.08206. And that's labeled in ATMs, liters, mole Kelvin. All right, so now the thing is what gives? Why are these things have such greatly differing numbers? And why do they have these crazy, crazy labels? Well, here's the deal. These two things are going to be the values for R that you're going to use when you pay attention to which pressure do you want, which pressure are you given. So the main difference between these two numbers is the units of pressure. So in other words, if we're doing a calculation where we're given a pressure in kPa, or we want the answer for pressure to be in kPa, we're going to use the top one. If we do a problem where the pressure is given to us in ATM, then we're going to use that number. Literally, all I want you guys to think of is it's a number that you're going to plug in. Now, there's some other things you got to pay attention to with this measurement and with this equation for today before I give you the equation. And that is, what labels can you use? Kind of on the last one, the last set of gas laws, the labels that we used were the only thing that we made sure we had to have was temperature had to be in Kelvin. Today, the labels are a little bit more specific, and we'll get into that when we get to the equation. So, all right. So today, when using this equation, you need to pay attention to pressure, volume, and temperature labels. This is where professors get you. This is where chemistry teachers get you. They're going to give you some measurements that you can't quite use exactly in the equation. And these are the little mistakes what's going to happen is some of you guys are going to be like, man, I'm doing everything wrong, but you're actually just making really little mistakes. The little mistakes are because you're not paying attention to what the volume or the pressure or the temperature needs to be labeled in to use today's equation. Okay, so I'm going to give you today's equation. We'll do a couple of examples, and that will be that. All right. So the ideal gas law equation, and by the way, tomorrow I'm going to give you guys a couple of variations of it. Today's gas law is going to be this equation here. You'll notice that there's no ones or twos. There's no before and after. It's just kind of everything put together. It is PV equals nRT. PV equals nRT. Okay? So PV equals nRT is the ideal gas law. I got a really dumb story I'm going to tell you that will help you remember this. I tell this to all my classes because this is how my classes typically refer to this equation. They don't call it the ideal gas law. I'll tell you what they call it in a second. I had a college professor at University of Nebraska, Lincoln. He had a professor or a mentor or somebody that was in his life during his undergrad years or graduate years. And this professor, this old dude, he says he's kind of an old, creepy looking dude. He was an expert in gas laws. Now, I don't know if this professor is making this story up, but this is what I tell people because this is what he told me. Well, anyhow, this old creepy dude since he was an expert in gases and did lots of calculations in gases, he decided to put the ideal gas law on his license plate. So on his license plate, think of a creepy old dude with that on his license plate. Now, that word, if you just spell it out, is Pivnert, but if you just glance at it, it kind of looks like the word pervert. And so the professors and all the undergrad students were kind of like, we didn't have the heart to tell him that we had this creepy old dude driving around in this car that had something that looked like pervert on the license plate. My point is, a lot of the times, students that I've had, and when I was in that class from that moment forward, I didn't think of this as the ideal gas law. I called it the pervert equation. So if you hear me say the pervert equation, This is what I'm talking about. All right. Now it's actually PivNert, but that's a pervert equation. So chemistry 2 students will tell you that they actually use this all the time, especially when you get into chemistry 2, because it kind of takes the stoichiometry stuff that you learned and it combines it with this gas law stuff. So we use this equation a lot in chemistry 2, and you'll use it a lot in college. So that's my stupid way for you to remember it. I swear to God, if you remember 3 things from me, you'll remember the urinal rule. You'll probably remember the pervert equation. I don't know what the other thing is, but I'm sure there's something. Maybe it's only 2. Who knows? Okay. So that's the ideal gas law. Now here's the big key. When using the ideal gas law, you have to pay attention to the labels. Okay. So some things I want you guys to understand. If volume is not in liters, you got to deal with it. So for example, if I give you a volume in milliliters, you would have to deal with it. Before you plug it in that equation, it's got to be in liters. Okay. N for right now has to be in moles. I'll show you guys some different ways in which we can deal with that. Okay. Temperature must be converted to kelvins if you want to plug it into this equation. If it's not, if it's in Celsius, you got to deal with it. Okay. And pressure is either going to be in ATM or kPa, depending on which R you use. So if we want to calculate a pressure, or we're given a pressure in ATMs, we're going to use that 0.08206. If we want to do a calculation in kilopascals, we got to use that 8.31, right? That's the rule. That's where this one's different. Here's where they get you. Professor will give you something in milliliters. You'll forget about it. You'll get an answer that's jacked up, and you'll be like, what happened? Why do I suck at chemistry? Why? Okay, so you don't. You just forgot one little thing. Okay? So the key is using the correct R. I would like to do a couple of examples with you guys today, just so you guys can kind of get a feel how these problems differ from the last set that we did. Okay? So here's an example problem. We want to find the number of moles of gas that have a pressure of 0.047 atm, a volume of 15 liters, and a temperature of 15 degrees Celsius. Okay? So find the number of moles of gas. Now, one of the dead giveaways that we have to use the ideal gas law here is because they actually ask for moles. And moles, all right, so what makes this stuff difficult? What makes this stuff difficult is when we combine and combo all this stuff together. You have the old gas laws, you have this gas law, and it's like, what am I doing here? Okay, so you'll know you're going to have to use the ideal gas law because they are giving you kind of all the factors and they're asking for the number of moles. Okay, so we're going to go through here. We're going to label each thing and we're going to make sure we can plug it into the equation. All right, so the ideal gas law is PV nRT. Okay, all right. We'll start with the pressure. Looks like they gave us the pressure as 0.047 atm. Okay. The volume is 15 liters. Okay. So far, so good. If that was milliliters, we'd have to deal with it. Right. A temperature of 15 degrees Celsius. So a lot of people in the gas laws assignment from a couple weeks ago made the mistake. They forgot to convert temperature into Kelvin. So we cannot use 15 degrees Celsius. We have to add that to 273. So we would, what is this, 288? So we would have 288 kelvins here. Okay, so we're going to use that. The question is about moles. We don't have a clue what that is. That's going to be what we're solving. Here is the key. The key is to use the correct value for R. You have 2 options, 0.08206 or 8.31. Here's how you decide. You're going to go back and you're going to look at your pressure. If the pressure is in ATM, then you're going to use the gas constant that has ATM. I'm not going to write the rest of that crap because I'm a lazy turd and I don't want to. All right. I'm just going to leave it like that. Okay. So here we have PV. We don't know what N is. We have R, we have T. Everything is in the correct labels. We can go ahead and plug this into the ideal gas law. So hopefully, I'm not going to write the labels here because I'm going to try to save some room here. I'm going to run off the screen anyway. Let's hit this again. Okay. So 0.047, 15. Hopefully your parents aren't sitting there listening to this class and going, why is he talking about perverts right now? Okay, I'm obviously going crazy with the quarantine. Okay, so we're going to solve for n. All this is glorified algebra. We're just going to divide some stuff. If you have the calculators, you guys can go ahead and do that at this time. Or just sit there and wait for me to do it because I'm going to do it anyway for the sake of having this down on video. 206 times 288. All right. So my answer in moles is 0. Okay, now I'm going to look at sig figs real quick here. Looks like we got 2, 2, 4, and 3. I'm going to use 2 sig figs here. So it's, my calculator says 0.0298, blah, blah, blah. So we have 0.030 moles of delightful gases right there. Okay, that's using the ideal gas law. We'll do one more example, and then I will post an assignment at some point in the next few minutes, and you guys can tear it up, okay? If you guys have any questions, like when I get done, I push stop on record. You guys can ask me as many questions as you want, or you can just, I guess, hang out and talk to each other, or talk to yourself, or whatever, okay? Let's try another one. So we have, what is the temperature of a gas at 500 kPa, 250 milliliters, and 0.120 moles? Okay, so now we're looking for temperature. So I'm going to go ahead and list over here if everything is legit. By the way, as you do more of these, I wouldn't expect you to do this stuff to the side, but for right now, I don't know, makes it a little bit easier. Okay, so what is the temperature of a gas? Now, if we do this right, our temperature should be in kelvins. So we're just going to leave it like that. If they wanted it in Celsius, we'd have to do a step at the end. But right now, I don't care about that. We ain't got time for that, right? The temperature of a gas. Now, notice I didn't give you what the pressure is, what the volume is, what all that stuff is. This is where you're going to have to know your labels. You're going to have to know and learn that kPa stands for pressure. So we're going to have 500 kPa there. Volume is 250 milliliters. Now, before we put that down here, we have to deal with it. The reason we have to deal with it is because the gas law that we're using, ideal gas law, has to be in liters because of that stupid constant that we're using. So 250 milliliters to liters, all right, you would divide by 1,000, okay? 250 milliliters divided by 1,000 is 0.2500. We're going to try to keep the same number of sig figs it has, liters. N is 0.120 moles. Now, we got to use the correct value for R. A lot of times people just flip a coin with this stuff, all right? Please, once again, pay attention to your pressure. Your pressure is in kPa. So you got to use the one, 8.31. I'm not writing all the labels down because I got everything else here. Like I said, we ain't got time for that. So now we're going to set this up. We're going to solve for T using the same equation. So we have 500 times 0.2500 is equal to 0.120. R is 8.31, and we're solving for T. We get done, it should be labeled in Kelvin. So, I don't know, man. It's just algebra, right? Okay, when I get done, temperature is, okay, so looking at our sig figs. 4, 4, 3, and 3. We're going to have 3 sig figs here, so I got 125 Kelvin, which turns out to be pretty dang cold. Okay. All right. There you go. So here's what I'm going to do. I'm going to stop recording. If you want to see another example problem, I will do one, not on the video or whatever. If you have any questions, you can hang out, you can chat, you can whatever. I don't care. You can ask each other how your math classes are going. I'm not sure what math classes you're in. I'm sure trig is delightful right now. So there you go. Or algebra 2. Sure, that's a fun time right now. So I'm going to push stop here.